Optimization theory is an important area of study. If you are interested in, let's say, finance, or so let's say if you are interested in topics like finance, or say machine learning, or say AI, or quantum computing, or in general say physics. So if you are interested in these topics, optimization theory is very important and relevant. It's an important area of research. And today we are going to talk about some of the basics of optimization theory. So we will discuss some of the basics. We will try to understand what does optimization mean, like what kind of problems are called optimization problems. And we will discuss two kinds of programs which are optimization problems. One is called linear program, LP, or linear programming, and the second one is called semi-definite programming, SDP. So LP and SDP. That's what we will talk about. So let's look at what is an optimization problem. So to talk about an optimization problem, you need to talk about two things. One is something called objective function, and here what you have something called constraint. So you see that you have this x, which can be a variable vector. So this x, maybe like it's better to denote it as x vector, or like it's x1, x2 up to xn, and each of the xi, they belong to R. So overall this x, maybe let's remove the vector here, I think maybe it's implicit. This x basically belongs to Rn, and this x that you have here is called optimization variable. So this x is basically optimization variables, and what you are optimizing, so let's say here for example you are minimizing, is called an objective function. So this f0 is an objective function, and the fi which go from Rn to R, these are constraint functions. So these are what we can call constraint functions. So you are trying to optimize, minimize here, let's say, an objective function subject to certain constraints. And the bi that you get here, these are called bounds. So on your constraint functions, you get a bunch of bounds, and that's how you talk about what is an optimization problem. So linear program is a special case of optimization problem where the objective and the constraint functions are linear. So the objective and constraint functions are linear, then we call it a linear program. On the other hand, it's called non-linear program if the optimization problem is not linear. Okay, so if this is linear, then you call it linear program. If any of them is non-linear, then you call it a non-linear program. Okay, so back in the time, people have been interested in what kind of programs are linear versus what are non-linear, but later they realized that maybe it's important to distinguish between something called convex optimization versus non-convex optimization. And this is because a lot of nice mathematics has been developed for convex optimization. So people over time got interested in this distinction between convex optimization versus non-convex optimization, though linear versus non-linear is also a nice distinction here, like like that we see a linear versus non-linear. So anyway, let's try to understand what is the meaning of convex optimization. And to talk about what is the meaning of convex optimization, you should try to understand what is the meaning of convex here. So which comes from something called convex set. So what is a set called a convex set? I believe we all, even people here, will know what is the meaning of a set. It's just collection of elements. But a convex set is a special kind of set where, let's say, if there are two elements, for every two element x1 and x2, if you take a combination where this combination coefficient theta is between 0 and 1, if you take a combination such as theta x1 plus 1 minus theta x2, this kind of combination, if it's inside the set, then you call the set as convex set. Geometrically what it means, that you take 2 points in the set, so you can take 2 points, and any line segment that connects them, all the points, these points, like they should be within a set. So let's say this is a set that we are talking about, this is a convex set. On the other hand, let's look at this set. Now for such a set, let's say if we take 2 points, let's take point here and point here, and let's connect them. Note that we get here a point. This point is not in the set. So then we can call that this object that we have here is actually a non-convex set. I mean like the set of such points which correspond to this object is a non-convex set. So there are some of the examples of convex sets just inside of a sphere. So you take any 2 points which are inside a sphere, connect them, all of them will be inside of a sphere. Line segment is trivially a convex set. Inside of any regular polygon, it's also a convex set. So I hope you understand what is the meaning of a convex set. Once we know the meaning of convex set, we just need to define one more object, which is convex function, to talk about convex optimization. Okay. So what is a convex function? So let's say you have a function from Rn to R. It's called convex if its domain is convex. So domain is some set and the set has to be convex. That is the first criteria. And the second criteria is that you take any 2 points in the domain and take their convex combination. So this kind of combination which we earlier talked about, it's called convex combination. So this is also called convex combination of x1 and x2. So you take 2 points which are in the domain and take their convex combination and evaluate the function at that point. The value will be less than equal to, you take function values and take their convex combination. That's what it is. Geometrically what it means, that the function will be always below the line segment that connects any 2 point x and y, so it's basically, it's like a, this kind of parabola kind of object. That's how the convex functions look like. Okay, very nice. So I hope you understand now what is a convex set and what is a convex function. Convex optimization is basically an optimization problem where you have, let's say, this is your objective function and these are your constraints, and the optimization problem is called convex if the functions f0 to fm and h1 to hp, they are all convex. In other words, an optimization problem is called convex if both objective function and the constraint functions, they are convex. So in summary, an optimization problem is called convex optimization problem if both the objective function and the constraint are convex. If both objective function and the constraint functions are convex, then we say that the optimization problem is convex. So this has to be convex and this has to be convex. If either of them is non-convex, then we say that the optimization problem is non-convex. Some of the common examples of optimization problems that are convex is linear programming and semi-definite programming. So linear programming sometimes is what people call, like this thing is what called LP, and this semi-definite programming is what people sometimes call SDP, semi-definite programming. Okay. So for linear programming, we already saw that the objective function and the constraint, they have to be linear to roughly to be called a linear program. For SDP, we will see like, what does it mean to be called, like uh, semi-definite program. So the main idea in semi-definite optimization is to generalize linear programming and associated feasible sets. So the associated feasible sets corresponding to linear programming is polyhedra. To the case where the decision variables are symmetric matrices and inequalities are to be understood as matrices being positive semi-definite. So we will try to understand like what this means. It basically saying that when you want to think of semi-definite programming and you know about linear programming, then you can think of semi-definite programming as a generalization of linear programming, where we take the decision variables and we consider them as symmetric matrices, and all the inequalities are basically matrix inequalities. If that is the case, then you can think of them as semi-definite optimization. There is more detail to it which we will discuss now. Okay, so linear programming, informally, it corresponds to minimizing a linear function subject to linear constraints. So you have some linear function and you minimize it subject to linear constraint. So the standard form of linear programming is given by C transpose X, minimize C transpose X such that Ax equal to B, X is greater than equal to 0. Here X, which belongs to Rn, are called decision variables. So what we have here, these are called decision variables, okay. And these decision variables will be in the case of SDP will be basically matrices. So what you do is that you are trying to minimize C transpose X such that Ax equal to B and X greater than equal to 0. This is a standard form, and often what will happen is that your linear program is actually not given in the standard form. So in that case, you have to convert it into standard form. So let's say you have been given a particular example of a linear program here, where you are trying to minimize 80x plus 60y. So you can think of them as it is in the form of C transpose, so you have variables here x, y, and so this is your decision variables, and you are trying to, and your C is basically 80, 60. So then you can see that like C transpose, call that capital X, will be 80x plus 60y. But you notice that your constraints, they are not in the standard form. Why they are not in the standard form? Because in the standard form you have equality constraint and this non-negativity constraint, but here we have inequality constraint. So clearly this is not in the standard form. So this is not in the standard form. So we can take this and convert it into standard form using something called slack variables. So we can take two slack variables, let's say S1 and S2, and using this we can convert our LP, which is not in the standard form, into standard form. So you see that we managed to write it as equality constraint and some bunch of non-negativity constraint. So this is in the standard form, and you can always take a linear program which is not in a standard form, and you can convert it into standard form. Okay. So earlier we saw that we had this LP, which is which was given as minimize C transpose X such that Ax is less than, Ax is actually equal to B, Ax is equal to B, and X is greater than equal to 0. So this was the standard form of our linear program. So one can call this also as primal form. So this is primal form. So this is primal form. So this is a primal form, and you can convert a primal form into its dual form. So you notice that you notice that you are doing minimization here. There exists a dual formulation where instead of minimization you look at something called this maximization. So in that sense it's dual. So this is the dual formulation. So this is the dual formulation. So here we are minimizing and here we are maximizing. So you notice the difference. Here you are minimizing and here you are maximizing. But you notice that there are these this matrix A and the vectors C and B which are common. So you have C, you have A, and you have B, and you notice that this is what is common in both dual as well as primal. So once you have been given, let's say, primal formulation, you can write it in the standard form. From there you can extract your C, A and B, and using that you can write the dual form. And similarly, given dual form, you can write the primal form. Notice that only the decision variables, they are different. So here the decision variables is X and here the decision variables are Y. Rest information is same. It's like basically C, A and B that we are using. Okay, so let's look at one example. So this is an example of an example that we just looked at. So here we had this particular linear program in the standard form. So you can here you have like another example in standard form. So this is a pure primal formulation. So you are trying to minimize a linear function subject to certain equality constraint and non-negativity constraint. And you can take this one, and from here you can extract your C, A and B, and you can write the dual formulation. Like for example, you can notice here that the C that we have, so first let's write the decision variables. So the decision variable corresponding to primal is basically x1, x2, x3, x4, right? So this is your decision variable, and the seed vector that you have is basically 1, -8, 0, 0. So that's how you notice that C transpose this capital X will be like x1 -8 x2. So you can see from here. Now you notice that the C which appears here in the objective goes in the constraint as bounds of the dual. So you see that like here we have 1 -8 here, the C here, that C goes in the bound like 1 -8, like 1 and -8 you see here. Okay, and actually similarly you can see that like this B which is here in the objective correspond to the bound here that you have in the primal LP. So you see that here you have in the bound you have 4, 6, and that 4, 6 appears here in the objective. So yeah, so basically the long story short, you can take your LP and you can extract your C, A and B, and then from there you can given a primal formulation, you can write the dual formulation. There is also another approach through something called Lagrange duality, and through that also you can get it. But here I am giving you I would say maybe a relatively straightforward approach where you just write it in the standard form and then use the fact that given such primal formulation, the dual formulation is given like this. So you have to just extract C and B and go from primal to dual. So this is one example. Oh, so this is the example that we were looking just now. So this was the primal and this was the dual, and this is your C, this is your B, this is your A. So this define your LP. You can optimize, let's say, this one, and you get the answer for, let's say, x star equal to 2, 2, 0, 0. And so this is called primal optimizer. So this is your primal optimizer. Primal optimizer. And the corresponding value that you get when you do C transpose X star is called primal optimal. So this P star that you get is the primal optimal. So the P star, the corresponding optimal value, is your primal optimal, which is minus 40 here. Similarly, you can solve for the dual program, and for the dual you have this decision variable, which is y1 y2, and this is the dual optimal. The y star that you get here is dual optimal, dual optimizer, and the corresponding d star that you get is called the dual optimal solution. So this y star is your dual optimizer, and then this corresponding value that you get is called dual optimal. Okay. So in this case, what you have is that a primal optimal is equal to dual optimal, and such a phenomena is called strong duality. Strong duality. Strong duality. Like the P star is equal to D star. Okay. So corresponding to this linear program, the feasible set is this thing called polyhedra. So you get this thing called polyhedra, and there's a very nice theorem called Minkowski-Weil theorem, which says that every polyhedra P is finitely generated. Basically, there's a bunch of points U1 to UR and V1 to Vs, and you take a convex hull of them. So convex hull is defined like this, and a conic hull of this, which is defined like this. So you take a convex hull and conic hull, and that is enough to describe the feasible set of linear program. So this is a good thing to keep in mind. Okay. So far we looked at what is a meaning of an optimization problem, what is linear program, what is non-linear program, and then what is the meaning of convex set. Then we looked at what are convex functions, and then what is convex optimization, non-convex optimization, and then we looked into the detail of this linear program, and there we looked at also primal and dual formulation, the standard form, and so on, and how to use slack variables to convert a given linear program which is not in a standard form in a standard form. Now, corresponding to the LPs, there is this very nice property which is called weak duality. So you notice that the corresponding to every primal feasible solution X, the corresponding primal value is C transpose X. And similarly, for the dual feasible solution Y, the corresponding dual value is B transpose Y. Let's look at the difference between them. When you calculate the difference between them, you will find that it's always greater than equal to 0, which means that the primal value, like for every feasible primal value, the dual, even the dual optimal value is below it. So it's like there is always a a difference. I mean this is always a non-negative. What we are saying that for the primal value is an upper bound on the dual value. So let's see how do we get it. So C transpose X minus B transpose Y can be written as C transpose X minus, for B we write AX, because we have we had AX equal to B, right? So we just write C transpose X minus AX transpose Y, and then from here you can actually write it as C transpose X minus X transpose. So here you have C transpose X minus, so it is X transpose A transpose Y, but C transpose X is same as X transpose C, so then you can take X transpose common, and this is C minus A transpose Y. But then this is always less than equal to, because A transpose Y is always less than equal to C, this is always non-negative. And this follows from the fact that these are the constraints that we have in the dual program. So because A transpose Y is less than equal to C, and x is greater than equal to 0, they implies that the whole expression that you have here is greater than equal to 0, which means C transpose X is greater than equal to B transpose Y, which means the primal, every primal value is an upper bound on the dual value. Okay. Finally, we would like to mention that sometimes, let's say, if the optimal value, let's say primal and dual, are such that like they match. So let's say C transpose X star is equal to B transpose Y star, then we call it strong duality. And whenever you have a strong duality, something beautiful happen. So if you see, earlier we saw that we had this expression and this is greater than equal to 0. But let's say we have a strong duality. So in that case, for optimal X star and like optimizer or primal optimizer X star and Y star, you have this expression equal to 0, means the gap is closing because we have a strong duality. But something beautiful happens here. Let's say if the primal variables, if the primal optimal variables, they are non-zero, then that means this has to be 0, which means these constraints which are in the dual, they have to be tight. So whenever a primal variable is non-zero, the corresponding dual inequality must be tight. This is what is called complementary slackness, which happens at strong duality. So with strong duality, you get this statement. Okay. So far we looked at many things, including weak duality and a strong duality, and now we will very briefly look at this thing called semi-definite programming. Okay. So linear programming is given as minimize C transpose X such that AI transpose X equal to BI. Okay, I slightly changed the notation, but I mean you get what I mean. And X is like a non-negative. Now you take your CA, you take your variable, this X, the decision variables which are vectors, and you replace that by matrix decision variable. So here X belongs to Rn plus. Instead of that, if your X belongs to set of positive semi-definite matrices, then basically what you have is this beautiful object called semi-definite program. So what we have here is actually a cone of positive semi-definite matrices. So by cone we mean that like let's say whenever so a set S, so whenever you or let's say a set S is said to be okay, just a moment. So in a cone C, whenever X belongs to C, then lambda times X also belongs to C, where lambda is greater than equal to 0. So this is what a cone means. So here we have cone of positive semi-definite matrices, because you can take positive semi-definite matrices and you can multiply it with any non-negative scalar and it will be still positive semi-definite. So in that sense we have a positive semi-definite a cone of positive semi-definite matrices. And then what we have here is a fine slice. So we have this cone, and that cone is being cut by like these linear, these affine constraints, and these affine constraint cut the cone. So an SDP can be thought of as an optimization of a linear function over the affine slice of positive semi-definite cone. So you can take a positive semi-definite cone, let's say it's like this, and then you take a slice of that. There will be like, I mean it's like a fine slice of a PSD cone, and then over that region, basically if you optimize a linear function, then what you get is called semi-definite program. Semi-definite programs have lot of application. They have application theoretical computer science, control theory, operational research, and many more different areas. So like they have been very useful. Even like calculating ground state of Hamiltonian, you can write it as semi-definite program. And there are many quantum algorithms also apart from classical algorithm that people have developed to solve STPs. So given a semi-definite program, let's say, this case is called a primal formulation, the standard form of the primal formulation. So here this x is the decision variable, then this c and ai, they are in Sn, and yeah, basically this notation means trace of x transpose y whenever we write like this. So for example, this is an SDP because you can write it using c, a1 and b in the standard form. So you can think of it there, this is what gives you a cone, and this is what gives you a fine slice of the cone, and here you are optimizing a linear function over the fine slice of a cone. And given a primal formulation using C, A and B, similar to LP case, we can again write the dual, and you can show that the similar to the LP case, you again have something called weak duality. So you take the primal value and get a difference of the dual value, and that is always greater than equal to 0, and the solution is similar to the proof is similar to what we get in the LP case. So for semi-definite programming, you have a primal formulation, and again you can get something similar, this dual formulation. So that's it. In this session, we talked about many interesting things, such as what is an optimization problem. We talked about what is a convex optimization problem, what is a convex set, what is a convex function. We looked at LPs, we looked at weak duality, strong duality, complementary slackness. We looked at SDPs. We looked at the primal formulation of SDP, dual formulation of SDP, weak duality for SDP, and so on. I hope you like this video. I will try to go in detail about optimization theory in future sessions. And if you like this video, then I would say please support us via liking, subscribing, and spreading the word around.